Good afternoon. This is from Dr.B.Vijayakumar, HOD of Physics, SNS College of Engineering. The same unit, magnetic and superconducting material, the another topic we discussed from today. This video, the topic 3, domain theory of ferromagnetism. So, the brainstorming questions is, what is ferromagnetic domain? And what is ferromagnetic structure? So we discussed in the introduction part of ferromagnetic domain. So this material, the very good example is iron, because the magnetization, unless they have been previously placed in external magnetic field, the Curie's theory is created to the form of individual magnetization of the field. The quantum exchange magnetization to the form of internal separation, that is called as a domain. So the domains are separated in a small region, that means small boundaries. Each domain is a form of one ports. So the spin magnetic moments wise, each domain and it become changed in a position of directions in a magnetic flux. So without field, the external field becomes in a zero. So it's act in random direction. The weak field is applied. The domain only to be changed. The strong field is applied. The domain wall, it becomes changed from that. So the moment of domain wall and rotation of the domain wall. So the first one, the weak field is applied. The moment of domain wall take place in a weak magnetic field. So the specimen of the magnetic moment increase, and hence the boundary of domain are displaced, so that the volume of the domain changes in the previous figure. The rotation of the domain wall, it becomes to apply of a strong magnetic field. When the external field is high, then the magnetization changes by mean of rotation of the direction of magnetization. So the domain theory of ferromagnetism is based on to the internal and external energy wise. So the four types of energy become involved to the domain theory of ferromagnetism. One is exchange energy, anisotropic energy, domain wall energy, and magnetostrictive energies. The first one energy is exchange energy or potential energy of the material, or magnetic field energy, magnetostatic energy. The interaction energy, it's making adjustment of the dipole alignment themselves. So the internal energy is very important, because the dipole of the free pole at the domain, an external field is produced around its configuration. It's a high value of magnetic field lines. So this is the exchange of flux in that magnetic. So the second one is an anisotropic energy. That means the magnetization, it's a form of based on the domain direction. It's a form of easy direction or hard direction. The easy direction of the magnetization to be applied of weak field in a hard direction of the magnetization should be applied for producing the same saturation magnetization along both the hard and easy directions. So this has become hard direction to easy direction and easy direction to hard direction. The example is magnetite. So the direction is formed in 1 0 0 and medium is 1 1 0. Hard direction is in a 1 1 1. And the same in saturation is form of the opposite direction. The hard direction 1 1 and the easy direction is 100. So this exchange of energy required in a magnetized the specimen along hot directions overcome to rectified. Domain wall energy or Bloch wall energy. So here we discuss thin wall or thick wall based on the wall thickness, that is a Bloch wall. So when a thick wall, the spin at the boundary of misalignment to the direction of spin charges. But in thin wall, the spin of the boundary charges abruptly, then the anisotropic energy become in a very less. So this is wide wall and thin wall. Then magnetostrictive energy, when the domain are magnetized in different directions based on the change of the dimensions. So thank you very much. This is a reference I prepared from this PPT. Thank you once again. We discussed in another topic in another video.